Hi, welcome to Ushendra's Engineering Tutorials. Yet another important video from the playlist Control Systems, deriving the expression for Kp, Ki, Kd in frequency domain, providing the compensation to meet the desired frequency to obtain. So what should be the proportional constant, integral constant and derivative constant? Designing a PD controller, PID controller, what should be the constant values in terms of in frequency domain, subjecting S is equal to j omega, uh, obtaining the values of all these three constants in terms of frequency domain, and yeah, to provide the required phase margin at a particular frequency, omega, required omega, what modifications to be done, introducing the compensator, PID controller, etc. So in order to go to the derivation straight away, the designing part, we have to have some prior, we have to have some important derivations. Individually, the expression for Kp, expression for Ki, Kd, right? So in that process. Uh, a small reminder which you have come across in block diagram reduction. What that block diagram reduction algebra says, if we have a system like this one, if we have a system with the transmittance g of s, if we have a system with the transmittance g of s, transmittance for input e of s and output u of s, the output u of s is given as is equal to input E of s multiplied with the transmittance G of s, isn't it? According to block diagram reduction algebra. So from this one, the transmittance G of s will be equal to U of s by E of s. Guys, we will come across this one like E of s, I mean U of s by E of s, that should be reduced to G of s in the ongoing discussion, right? So remember this one. And another reminder, like it may be like if we have a complex term a plus jb, a complex term a plus jb, real plus imaginary, we have to reduce this to it's a magnitude a plus jb and phase angle a plus jb, phase angle, okay, phase angle a plus jb. So this is a, remember even this one also, we will make use of this one. And coming to the actual derivation which we are in search of, Kp, deriving expressions for Kp and Kd. So considering a system, okay, considering a system whose output is proportional to input, whose output u of t, and let the input be e of t. Guys, some authors, we have different authors, some authors will be saying that simply input, they'll be sticking with this one, simply input, and some authors they say error input, right? So for convenience, I'll be sticking with just input, right? So output is proportional to a system, considering a system whose output is proportional to input. So what sort of system? What is that practical system? Simply a resistive network, uh, resistive network like this one, simply a resistive network. The output is directly proportional to input. So how can that be put in a statement, like in an equation? We can say that resistive network. You may ask me, what is that practical network? Resistive network. Now u of t, how can that be? U of t directly proportional to e of t, right? So putting that in an equation, and we cannot go ahead with this one, we need to have a constant of proportionality. So u of t is equal to e of t as it is, some constant of proportionality k, constant of proportionality, direct output is, we thought for output is directly proportional to input, so it's a kp, okay. And such system whose output is directly proportional to input, we call it a proportional system p, okay. So here, and yet another system, uh, whose output u of t is directly proportional to the first integral of the input. I repeat, considering a system whose output u of t is directly proportional to the first integral of the input. So what sort of system is that? Low pass RC network, low pass RC circuit. It can be with the derivation, it can be proved that output is the integral of the input, right? So RC network, low pass RC circuit, low pass filter, low pass RC network, that could be proved that output is directly proportional to input, right? So in that case, how to put that in a equation? U of t is directly proportional to the first integral of input E of t dt. So constant of proportionality, u of t is equal to k integral E of t dt. Okay, so it's an integral function, so we have ki. Okay, and on the other hand, guys, considering low pass, output is directly proportional to the first integral of the input. So high pass, another circuit, another network, another system whose output u of t is directly proportional to the first derivative of the input. What I say is u of t is directly proportional to the first derivative d by dt of e of t. Just reverse this one. High pass filter, we can prove that with some derivations. We can prove that high pass filter, the output will be directly proportional to the input, and u of t, in this case u of t will be equal to k, constant of proportionality, I mean the constant, d by dt e of t, okay, and d suffix d. So this one, now this is proportional system, and this is integral I, and this is derivative system d. So we have what we want if we need a PID controller. The combination of all these, a PID controller, is that a system whose output is directly proportional to the input plus directly proportional to the integral of the first integral of the input, and which still plus which is directly proportional to the first derivative of the input, and combining all this we have a PID controller. So what is a PID controller? Output u of t is directly, I mean straight away, combination of all this proportional plus integral plus derivative, that gives a PID controller. So what we have, u of t is equal to kp e of t plus ki integral e of t dt plus k d by dt e of t. Okay, so this is the one. And guys, we have integration over here, we have a derivative function over here. So it will be tedious if you go ahead with the time domain. So the very convenient way is to convert the time domain function to a frequency domain, time domain to frequency domain. That will be easier, right? So what to do? Considering the Laplace transform of the above expression, this one, the Laplace transform of this one, and here to go to the next step, you have to have a basic fundamental, that Laplace transform of integral function, Laplace transform of derivative function, the properties of Laplace transforms, right? So guys, Laplace transform of x of t will be x of s, Laplace transform of u of t will be, as u of s here, u of s will be equal, it's a constant, nothing to do with that, no Laplace transform for that, kp, and here x of t, x of s, e of t, it should be e of s, the Laplace transform of e of t, plus ki as it is. As here we have a property of Laplace transform, a property of integral function, Laplace transform of integral function. Check that one, ki as it is, it's a constant, ki e of s by s, integral Laplace transform of integral x of t dt will be x of s by s. So in that case, neglecting the initial condition, okay, so u of s by s plus kd as it is, okay, the Laplace transform of first derivative of function, Laplace transform of d by dt of x of t, that will be s into x of s. So we have s into e of s, making use of the properties of Laplace transforms. And guys, we have e of s in all the three terms as common, e of s, e of s, e of s, taking that out as common and pulling into LHS, that gives us u of s by e of s here, which will be equal to kp from here plus ki by s from here plus s into k d from here, and this is. So guys, in the beginning itself, I said something right regarding block diagram reduction algebra, u of s by e of s from over here, that this entire expression could be written as g of s. Okay, u of s by e of s, output by input, and now this one, it's we exercise on this one, this expression g of s. Guys, simply it's not g of s, more precisely, because this is the transfer function which provides the compensation to meet the requirements. Introducing this one, introducing the PID controller, we obtain the desired phase margin, etc. Right, at a particular value of omega, s is equal to j omega. So more precisely, we have a suffix for this, gc of s. Okay, gc of s, which provides compensation, and so, right, make a note please. Guys, this one, gc of s will be equal to kp plus ki upon s plus s into kd. So whenever we have the term s in the equation, that becomes complex. Why? Because we'll be plugging in s is equal to j omega, isn't it? S is equal to, we'll be plugging in s is equal to j omega, which says we have plus the real term 0 and we have the imaginary term. So it's a complex function, and that has to be converted to like this one. We have to write that in terms of magnitude and phase angle. So we will be having for this expression, because it's in the s domain, it's in the Laplace domain, it will be a complex function, and we have to obtain the magnitude and phase angle of this given function. Let's say the magnitude, like here, magnitude gc of s, and on the other hand we'll be having phase angle gc of s. Guys, magnitude always that could be represented with a, isn't it? That's always magnitude a, and more precisely ac, suffix c, for compensation. Okay, and on the other hand angle gc of s, let that be angle theta. Okay, so guys, this is the conversion. On the other hand, not only this one, we will be given with the open loop transfer function to which we have to provide the compensation. The open loop transfer function, the phase margin will be something else, and introducing the controller, compensation controller, PID controller or PI controller, PD controller, we have to obtain the desired phase margin. So we'll be provided with the open loop transfer function also, and that value of omega at which we have to meet all these desired frequency, all these requirements. So we'll be having g of s also. Simply g of s, open loop transfer function, will be given. Guys, we will solve a series of numericals, designing a PI controller, PID controller, etc. Right? So then you can, while solving numerical, you can have an idea of what is that gc of s and what is that g of s. Right? So open loop transfer function will be given. Even the open loop transfer function will be having, it's again associated with s, which is a s domain. I mean, it's a frequency domain. So even this one, even the open loop transfer function will be complex in nature, and that has to be produced, that has to be transformed to its magnitude and phase angle term. So here, so what we have is, even this one, g open loop transfer function has g of s, magnitude g of s, and phase angle g of s. Right? So guys, magnitude, it's a, and phase angle, it's theta again. This isn't of the significance here, it's a theta. Okay, let that be. But here we had a suffix c saying that it's a magnitude of the transfer function providing the compensation, isn't it? So we need to have a compensation, I mean, we need to have a suffix for this one, saying it's not simply a, but it's a1, and we have a specific, there is a Yeah, we have something, we have it's somewhat related to the design part. So this A is a magnitude of the open loop transfer function at omega equal to omega 1. Okay, so guys, this is highlighted. This will be, you could understand only while doing the numerical, right? So it will be asked, we need design a PID controller so that it has a phase margin of something at a particular value of omega radians per second, right? That will become omega 1. So we will assume that to be omega 1, and when this value is plugged in over here, we'll be having a magnitude, and that will be A1, right? And guys, another important point to be highlighted, remembered whatever in this design, especially in deriving the expressions for or designing a controller, compensation controller, the design is carried in such a way that the magnitude of this one, of the system which provides compensation, and this one here, this one, I've changed the color, so try to understand this one. I will write over here, I don't erase it, I'll stick to that, I'll prove it. So what the design is, AC, okay, the magnitude of the system who's I mean the compensator system, into A1, the magnitude of the open loop transfer function, plugging in the value of omega equal to omega 1, that value of frequency at which the desired modifications is to be done, will be equal to 1. Guys, I'll prove this one, okay? I'll stick to this, I won't erase this. I'll be solving in numerical, I'll prove that. Once again, I repeat, it's the magnitude of the compensation, the system which is providing compensation, a PID controller, and A1 is the magnitude of the open loop transfer function, plugging in the value of omega equal to omega 1. Okay, from this one what we have is AC, from here AC will be equal to 1 by A1. Okay, AC will be equal to 1 by A1. Now this could be, this ratio could be plugged in over here, the same AC, isn't it, which we are talking about. So that will be 1 by A1, right? From here AC is plugged in with 1 by A1 from this one. Yeah, this will be proved, the product AC into A1 equal to unity, that will be proved. So AC plugged in with 1 by A1 and theta as it is, this theta. And on the other side what we have, this is yeah, this is for, I said we'll plug in that one. So guys, when this happens, 1 by A1, when this magnitude comes in, when omega equal to omega 1, okay, so we have this one in the sense already omega is plugged in with omega 1 over here. So that, did I confuse you? I said we somehow arrived to 1 by A1, right? And 1 by A1 under what condition? At omega equal to omega 1. So we have already plugged in omega s is equal to j omega, not simply j omega but with j omega 1. So taking that transformation, what we have is kp plus ki by s is plugged in with j omega 1, okay, plus j omega 1 kd. Guys, hope you understand the script. Yeah, my previous video, the script was very poor. Please comment if there is any problem with the script on the board, okay? So guys, this is the final transformation. How did we get this one? From this design. And from this design what we have, AC is equal to 1 by A1. So plugging in the value of AC is equal to 1 by A1 over here, and theta as it is, the phase angle, right? Now going ahead, so guys, what it is simplifying for this one. So j omega 1 from here will be equal to j omega 1 kp plus, simply it's a ki minus j into j, that will be minus 1, right? J into j minus 1 into omega 1 square k d, that will be equal to, guys, 1 by A1 angle, phase angle theta. Okay, so this one I'm putting it in a bracket. Yeah, I have a reason for that one. 1 by A1. So guys, it's dividing, shifting that side, it will be multiplying. So guys, here a small modification over here. I don't want to write another step over here. So this I'm dragging it to RHS. Okay, so this one I'm dragging it to RHS. This one over here. In the sense, j omega will be over here. J omega 1, that will be here. So I'll be this, we don't need anymore over here. So guys, here, so which will be equal towards that j omega 1, which was over here. I pulled it to RHS, and so guys, more precisely, it's a 0 plus j omega 1. It's a complex function. Okay, so complex function we have to express in terms of magnitude and phase angle. So in that way, what will be the magnitude of this one? Guys, magnitude, it's a 0 plus j omega 1. The magnitude will be equal to under root 0 square plus omega 1 square. Now 0 is invalid, in the sense we don't have this anymore, omega square and this one. So magnitude will be left with omega 1, right? So magnitude will be left with omega 1. What about phase angle? Phase angle will be equal to tan inverse omega 1 by 0. That will be tan inverse infinite, which will be equal to 90 degrees. Omega, anything by 0, that's infinite, isn't it? Tan inverse infinite, that will be 90 degrees. So guys, the magnitude will be only omega 1, the magnitude omega 1, and the phase angle from here, it will be 90 degrees phase angle from the first function, and from the second function 1 by a1 phase angle theta from the previous expression. And we have j omega 1 kp plus ki minus omega 1 square kd on the LHS. Guys, magnitude should be multiplied and phase angle should be added, isn't it? So what we have is magnitudes are multiplied. I'm erasing this one, don't worry, we have that expressions. Magnitudes are multiplied, so what we have is omega 1 by a1, and the phase angles are added, so angle 90 plus theta. Okay, so these are the expressions. And guys, I need this place. Okay, I need the place to explain something else, to give a justification for something else. So guys, over here, now this 90 plus theta, that could have the modification over here. Okay, omega 1 by a1 as it is, and this 90 plus theta, this 90 plus theta, that could be written as cos 90 plus theta plus j sine 90 plus theta. Okay, over here. So this one, cos 90 plus theta plus j sine 90 plus theta. Guys, how can that be written? So from here, a small explanation for that. Guys, now this entire expression, now here, now this is completely our real part, and this is our imaginary part. Okay, writing the phase angle equation for this one, theta will be equal to, from this one, what we have is b by a, isn't it? How I'm explaining how this could be written, expressed in terms of this one. So from here, if we have to write the expression for the phase angle of this one, theta will be equal to sine this entire jb, isn't it? Sine 90 plus theta by sorry guys, a small modification over here. So guys, theta, from the writing the to write the expression for phase angle theta, what we have is tan inverse b by a, isn't it? Sorry for the mistake over here. We have theta equal to tan inverse b by a. Now b is our sine 90 plus theta, this one, by a part is cos 90 plus theta, isn't it? So guys, what is this? It's a sine by cos. What is that? Tan, isn't it? So theta will be equal to tan inverse tan 90 plus theta. So guys, this is the modification. Over here, what happens is, what the consequence is, tan inverse and tan gets cancelled, and the theta will be 90 plus theta. So we came back to this one again. While expressing this in terms of phase angle, we'll come back to, okay, we may express this in terms of cos 90 plus theta plus j sin 90 plus theta. When we write the expression for phase angle, that comes back to this one, and so this could be, yeah, this is right. So guys, so this can be written in terms of this one. Okay, so this is the justification. So what happens next is, here and here, omega 1 by a1 as it is from over here, cos 90 plus theta, that will be minus sin theta, and plus j sin 90 plus theta, that will be simply cos theta. Okay, so guys, that's the modification. Over here we have j omega 1 kp plus ki minus omega 1 square kd over this side, right? So this is the expression, and yeah, we are almost there, guys. We have real terms and imaginary on either side of the equation, of this equation. We have imaginary and real on either side of this one. So equating that one, what do we have? We have guys, imaginary over here, j omega 1 kp. This is the only imaginary of this side. Okay, j omega 1 kp on this side will be equal to that same imaginary j omega 1 cos theta by a1. So j omega 1 by a1 from over here, this has to be multiplied, isn't it? So j omega 1 by a1 cos theta. Okay, so this is what, and something gets cancelled on either side. It's a j omega 1 and j omega 1 gets cancelled, so we have the expression for kp, which is equal to, guys, cos theta by a1, expression for proportional controller p, right? kp expression for kp cos theta by a1. On the other hand, equating the real terms, what is that? ki minus omega 1 square kd will be equal to, this is, we are done with the imaginary, so the real part will be minus of omega 1 sin theta by a, guys. Okay, and another small modification over here is ki plus this side, shifting it this side, omega 1 sin theta by a will be equal to omega 1 square kd. Okay, omega 1 square kd, and if you want to have the expression for kd, what it is ki by omega 1 square plus sine, guys, it's a a1, isn't it? A1, sorry, suffix a1, sine theta by, what do we have? a1 by omega 1. Why? Because when this comes over here, omega 1 and that square gets cancelled, and this expression. So guys, something important point to be revealed over here. If only PD, if you have to evaluate only PD, proportional plus derivative controller, ki should be assumed to be 0. We don't have this anyone, so we'll make it, we don't have this term. This term is made 0 if we have to design only PD controller, making use of this expression, right? And on the other hand, if it's a PI controller, without the derivative, if you want to have a PI controller, in this expression, KD is assumed to be 0. Ki equal to minus of omega 1 by a1 into sine theta, right? And like that. And guys, if you want to have a PID controller, PID control, which involves proportional KP, KI and KD, what the expert suggests is, in the question itself you will be provided with omega 1. You have to go in search of which is the value, what's the value of omega equal to omega 1. It will be specified. Okay, and important point is how to evaluate the value of theta. As the phase margin that will be mentioned, so this is the phase margin to be designed, that will be in the question itself, that will be desired phase margin. Okay, desired phase margin, it will be specified, we need to have this phase margin, so that will be desired phase margin minus phase margin of the uncompensated system at omega equal to omega 1. That will, this result will give us the theta. I repeat, we need to have theta, isn't it? Okay, cos theta, that's fine. A1, that was explained. Magnitude of the open loop transfer function when plugging in the value of omega equal to omega 1, that gives us A1. Magnitude of uncompensated open loop transfer function, that gives us A1. Okay, that gives us A1. So how to get the theta again? I repeat, the phase margin will be specified in the question itself, and we need to have design a PID controller to have so and so phase margin. That will be the desired phase margin minus the phase margin of the uncompensated system. We exercise on the open loop transfer function G of S. The open loop transfer function G of S, we obtain the phase margin of the open loop transfer function, and that will be the phase margin of the uncompensated system over here. That will be over here. So the difference will give us the theta. That theta we will be having the theta from this very expression, and A1 and omega 1, that will be specified. Yet another important reminder is that, guys, while designing PID controller, the expert says go for, the question will be in such a way that design PID controller to meet so and so specifications along with meeting the given steady state error. Yeah, you need to have an idea on a steady state error. What is a steady state error? ESS, that will be equal to 1 by kV for a ramp input, and that will be 1 by Ka for a parabolic input, if I'm not wrong. Velocity error constant, and acceleration error constant. Guys, this will be, we have to evaluate Kv in order to evaluate Ki. Then the value of Ki is plugged in over here to evaluate Kd. Guys, remember that step. If at all we have to design a PID controller, Ki has to be evaluated first, making use of the steady state error values. So why only Ki should be evaluated first? Going back to that expression, I hope you remember this one. Yeah, these are the expressions for that one. Okay, I need this place. If you remember, we have this one, Gc of S is equal to Ks into Kp plus Ki plus S square into Kd by S. Okay, so if it's a first order system, it will be, if it's a type 1 system, this will be gets cancelled with why? Because we have Kb for a ramp input, Kb equal to limit S tends to 0 S into, yeah, the steady state error should, design should be in such a way that the steady state error requirement is met after the compensation is provided. Okay, so Kv will be equal to Gc of S into G of S after providing the compensation to the open loop transfer function. Now this one. Okay, so in that process S gets cancelled and somehow, and even this becomes 0. Why? Because we have to plug in limit S tends to 0, isn't it? So S is equal to 0, that becomes invalid, and even Kd becomes invalid. Only we'll be left with Ki, and in that process first the Ki should be evaluated while we design for PID. The design is for PID controller. If it's for a proportional PI controller, yeah, evaluate for A1, omega 1 will be given A1, with that value of omega 1, A1 will be evaluated, and obtaining the phase margin of the uncompensated system, that gives us theta, and so we can go ahead. But this to be remembered while we evaluate for PID controller, we have to evaluate Ki first, making use of that, meeting that specification for the error constant, steady state error, to meeting Ki, that value of Ki which can meet the particular steady state error value. Right? Did I miss something? No. We have theta. How to evaluate theta? This one. A1 over here. How to evaluate A1? Plugging in the value of omega equal to omega 1 for the expression for magnitude of the open loop transfer function, that gives us A1, and yeah, Ki from the steady state error, given steady state error, that gives us Ki, and plugging in the value of Ki over here, that gives us Kd, and Kp we'll be having theta, so that gives us Kp. That finishes. Okay, so hope you understood the derivation. Here we have to focus on this, we have to remember this expression, and we have to remember this expression. Okay, this one Kd, for the expression Kd we have this, and Ki from over here, making use of this one 0, or else, yeah, let's say in the numerical, while we go for a series of numericals in designing PID controller. So hope you understood the analysis. Please support me with your valuable share and a subscription. Thanks for watching.